So the homework 1 grades, they'll be posted within a week. So our target for every homework, which I'm hoping we'll be able to hit every week or for every homework, is 1 week for grading. So if Friday comes around, if the end of Friday comes around and you still don't have your homework 1 grade, that's when you can start complaining and start yelling at myself and the TAs and saying, "Hey, get your stuff together." We're set up for it. We're starting the process. We've done some initial analysis, and we're getting underway with homework 1 grading. Homework 1 grading shouldn't be too difficult. The bulk of the time is spinning up the Docker containers, so we should be able to get this one through pretty quick. Yeah, and Google definitely hires on talent. If you can write code, I'll say this during the lecture part 2, just so it makes YouTube. If you can write code that works for a company, you're going to get a job. Companies, especially software companies, like to make money, and software companies make money by having software that works, that people want to pay for. If you can produce that for them, they're going to hire you. If you can't produce software, then you have bigger problems. If you cheesed every assignment, if God forbid you actually cheated and got away with it to get your degree, you're gonna have a tough time getting a job. If you've complained through every assignment and just did the bare minimum and said, "Oh, this sucks," you might have a tough time getting a job. If you take your studies seriously and actually try to learn what your professors are teaching you, you can walk into Google and just say, "Hey, I'm here. Where's my money? Where's my desk? I'm going to write some software for you," or whatever company you want to go into. All right. So let's talk about encoding again. So today's all examples. Actually, I do want to start at the slides just to do a quick recap of what we're talking about. And then I'm going to go into the code. I'm going to try to show several different languages and just kind of play around with this. This is going to be a live examples day. So deployment in Docker. Oh my goodness. Static files, Mime types, and encodings. So we saw all the stuff that we need to know for objectives 1, 2, and 3 for homework 2, but it went by quick. I mentioned it and then went on, and a lot of this will be figuring out how to do this stuff in your language, which a lot of the course will be. How do we actually take this content and apply it to our code, which is what today's for, is showing in different languages just how to do this stuff and how to work with it. So we learned about MIME types. Nothing too much to MIME types. The content type header needs to be set to the correct type that you're sending. So if you're sending an HTML document, your content type better be text/HTML. And you can add extra information if you want to make sure the browser is rendering this as UTF-8. I actually just had an issue with this where a browser was not defaulting to UTF-8. I did need this char set. So if you're having issues with that, with your Unicode, your UTF-8 not rendering in the browser, make sure you do have this char set to make sure that, hey, browser, it's freaking 2021. What are you doing? But hey, this is UTF-8. Get your stuff together. If this isn't here, I'm not sure even what the default, what it uses for the default char set. I have a suspicion that it goes off of your operating system's default character set. Because I had that issue on Windows, of course, which likes to use its own encodings. MIME type sniffing is important, so make sure you have this X content type options no sniff for security reasons. And then the big thing that we need to think about and talk about and explore today, and that I want to do demos of, is character encodings. So when you have information that you want to send over the internet, it has to be binary or bytes, that, as we'll see in our code, and then the bytes are sent 1 bit at a time over the wire or over the fiber or over the air with Wi-Fi. So we have to encode characters in binary in some way. We saw ASCII to do that, which maps characters to their hex to their byte values. We can look at the hex column to look at those bytes directly. And each character maps to one of these values. It maps to a number, effectively. That's not quite enough because we can only encode those 128 characters. It's great for English, but not much else. So we pulled in UTF-8. UTF-8, the important thing here is that not all characters are represented in a single byte. If a character is represented in a single byte, that means it's an ASCII character, so all the ASCII characters are 1 byte long, which, when we're computing our content length, the content length is always the number of bytes of data that we're sending. So if we're sending ASCII text, ASCII only text, which we did for homework 1, and which is not true for homework 2, we'll be sending some UT8 specific characters. Then if it's only ASCII, then the length of the string is equal to the number of bytes being sent. So we can get away with checking the length of the string if we only have ASCII characters. As soon as we have a non-ASCII UTF-8 character, that character is going to be multiple bytes, either 2, 3, or 4 bytes. So there's no easy way to take the length of the string and figure out how many bytes that string is represented in. So, like, if this were always 2 bytes, maybe we could just try to times by 2 or something. We can't really get away with any of that because it's either 1, 2, 3, or 4 bytes when we're dealing with UTF-8 characters. So we need to make sure that we're measuring the number of bytes of the string, not the length of the string. And you've heard me say this at least, I don't know, maybe 10 times by now, at least 5 times by now. There will still be students on homework 2 who don't do this, who do string.length, give me the length of the thing. I'm trying to say it enough times so I don't see that question in office hours this semester, so we can focus on the deeper content. But we will explore this a bit more, and I'll show examples and demos of this. These character encodings are very important. So when we want to send a string over the internet, encode it in its UTF-8 bytes. The internet doesn't understand characters, it understands bytes. So we're going to encode this with UTF-8. When we receive bytes over the internet, we're going to decode them into strings. And the big takeaway is setting that content length to be the proper length. This is what we really need, the content length to be proper. So that's my quick recap. Let's explore this. If I can get the right window open. Should be this one. Let's full screen that. Let's make this nice and big. That should be fine. Reload the window switching between language servers. Oh my goodness, my cursor's not able to be seen. Oh, that's going to be a struggle. I can see it if I look at the monitor, the screen that I'm capturing, but when I'm looking at it through OBS, which means what you're seeing too, the cursor is almost invisible. So let's take a look at some encodings. Let me leave this expanded too. Let's take a look at some encodings, and I will start with Python. It seems to be the most popular by far. So I took a look at the homework 1 submissions. I just did some quick analysis of it so far, and the languages that y'all chose, I mean, this might as well just be a Python course. I'm still going to mix up the examples, but 91 of you chose Python for homework 1. Now, mind you can still switch your language. If you ever switch your language between homeworks, that is allowed, but just keep in mind that you will have to rebuild a lot of the stuff, a lot of the foundational stuff that you built. So you might have to redo big chunks of homeworks 1 and 2, for example, if you switch at homework 3. So just a heads up on that. Or you can stick with Python, those of you who chose that. But if you want to move away from Python, do that too. 91 of you chose Python. 15 of you chose Node, so there is a good representation of JavaScript out there. And I'll start showing more JavaScript examples to reflect that. And then that's about it. 2 of you chose Java, 2 of you chose C#, and 1 brave soul is doing the course in Go. Which, if you do the course in Go, you will learn a lot more. None of my examples are going to be in Go, and sorry, none of my examples will be in C# either. But I will show Java, which is very similar to C# in a lot of ways. Go, I think you will learn a lot. It's a very useful language. But I'm not going to show examples in Go, so maybe someday. It's not going to happen this semester. Go Power Ranger. Fortran gang. No, Fortran. Nobody did Fortran. Or Fortran. I think I was saying Fortran. But those are it. Only 5 total languages represented. 0 Scala. So I will keep sleeping on C#. That's right. 0 Scala. I was kind of surprised to see that. So let's get into some content. Let's start with Python, since that's what's going to hit most of you. I want to go through this example where I'm going to play around with encodings. And let me get this up on the screen. Encodings, Python 3, which you have no idea how good it feels to just be able to type that right in VS Code. For some reason, that's surprisingly difficult to just set up Python. Finally realized, just like the previous lectures, I just went to Ubuntu. So you can open up VS Code in your Ubuntu environment, and now I just have a bash shell. I can write bash scripts and not have to think about Windows. I was in PowerShell. I installed like 4 different versions of Python, and none of them, like I had to add them to my path, but I couldn't figure out where they install to. Finally, I'm just like, I need to get away from Windows. But anyway, somebody who's more well versed in Windows, I'm sure that's not an issue, and you're just like, just hit the F12 key. But you know what? I couldn't. I had to cut my losses and stop spending time on it. So we're just using bash, which is all I ever wanted. So I wrote this method, which is going to show us a lot of things that are going on with these encodings. So, and I'm going to call this method on various strings. I'm going to start with just hello. So let's focus on this one first and talk about what this code is doing and what this is showing us. And I want to peel back the encodings and show you what's going on with your strings. That's the goal of this example. So, show encodings, where X is going to be just the string hello for the first example. Let's go through and see what this is doing. So first, Python has nice encode and decode methods. One of the reasons why a lot of you chose Python, and I think I have been pushing you towards Python a little bit. It is, it does make certain things easier to work with. One of those things is encode and decode. You just have, if you have a string and you need it to be UTF-8, you just do .encode UTF-8. And if you leave UTF-8 off and just do encode, it will, I should say in most cases, default to UTF-8. If you want to be safe, just specify UTF-8 and you don't have to think about it. That's going to give us this string, but encoded as a byte array. I wonder if I can actually very quickly. What is it in Python? Is it type of? I think that's JavaScript, isn't it? Encoded that. How do I get anybody know off the top of their head how to get the type of an object in Python? I don't think it's that. Oh, type of. You know what? That's why I love Python. How do I get the type of? Type of. Just makes our lives really, really easy. Thank you for that. Like I'm literally saying it, type of, just type of. Read it as a function called type of X encoded. So anyway, I'm going to encode this as UTF-8. This should be a byte array, or an array of bytes, or a list of bytes, whatever Python has it as. But this is going to be bytes, or byte string, I think it is in Python. This is going to be a byte string. A string is an array of characters. A byte string is an array of bytes underneath the hood. So we have a byte string. So we have a byte string. If we print out, we're just going to print a few things to the screen. The string, as a string, just X, straight up a string, that's going to print exactly what we expect, just hello. Hopefully you're following me that far. Nothing new there. You've been doing that since day 1 of 115. Next, I want to print out the byte string, which is going to be a little different. So I'm going to print out this byte string, which is an encoded string, which is just bytes. It's strictly just bytes. So I'm going to print this to the screen. I'm going to convert it to a string first, just so it can print, just so it can be displayed. And it's going to print a little bit differently. It's going to have this B, and then in quotes, the string that I have. This is Python's way of saying, hey, this is a byte string. I decoded it for you just to print to the terminal, just to print for us, for our human consumption. But this is just an array of bytes, or a list of bytes. So we have this list of bytes. Python's going to be like, look, this is just bytes, but this is what it does decode to if I use the default encoding of UTF-8. I'm going to show you what this is going. Actually, no, that's not using UTF-8. Say, obviously, right here, it's not. But it is doing some help for us, just so we can see what's being, what it is. So let's peel this back a little bit more and see what's going on once we encode a string, what this byte string is. So I want to print this out a few different ways. First, the decimal values of each character, of each byte in this byte string. So for this, I'm going to iterate over the bytes and just print them out. By default, Python is going to print these out as decimal numbers. A byte, it's a 8-bit binary representation of a number. If you print it to the screen, by default, it's going to print as a decimal number because Python is going to do some conversions for us. Again, just for our human consumption, so our eyeballs can see numbers that we're used to. We're used to base 10 numbers. So if we print this out, we'll see the base 10 values for each character after it's been encoded as a UTF-8 string. Next, I want to do the same thing, but print out in hex. So here, I'm going to override the default. I'm going to say, no, don't print these for my consumption. Print them out as their hex values. So Python just going to do hex and convert each byte into a hex representation and print those to the screen. So I can get the same information, but as hex. And the notation for hex always start with a 0x and then the hex characters. Each hex character is 4 bits, so we get 2 hex characters for each byte, representing like this. I'm sure you can recall back to somewhere, probably back to 191 last time you saw these, right? How often do you see these? And then I'm going to do the same thing, but in binary. So I want to take those bits and just show the bits directly. So with this, I'm going to use the binary function, and which will format this byte as bits, as it's 8 bits, and show me exactly what those 8 bits are. And these are the bits that are going to be sent over the internet when I transmit this byte string through my TCP socket. The notation, this 0B, is just to say, hey, these are bytes. This is binary. The 0B is going to precede every one of these just for our consumption, so we know that this is supposed to be binary. We wouldn't want to read this as 1.1 million. We want to make sure, Python wants to make sure that we know this is binary and that we should read this appropriately. So the binary bits of the string hello, and there we go. What is the end space? So by default, if you print something, use the print function in Python, it will end with a new line. So it'll print whatever you give it and then a new line character. So effectively a print line in other languages. I can override that behavior with end. End is going to replace that new line with whatever character I give it. So if I replace it with a space, I'm printing this and then a space, so I can get these printed, then a space, then the next iteration of the loop, print the value with a space, just for my formatting so I can see it, so I can get this in a way that's more legible. Since we added a line, let's run this again. Oh, the class is just bytes, just strictly bytes. They're just bytes. I mean, that's what we want. That's accurate. They're just bytes. So let's take a look at quick thing here. No, I don't want it on that monitor. Doing this with dual monitors is so precise. And I want to pull up the ASCII chart just so we can verify, just so we can see exactly, make sure we're getting exactly what we expect. So with the string hello, we're starting with, I believe I did it all lowercase. Yeah, we're starting with a lowercase h. The decimal value is 104. The hex is 68. 104, 68. Like, things are matching up. We're feeling good about this. And we can go E101 is the decimal representation, 65, 101, 65. So we're feeling good. We actually are getting the ASCII encoding of this. It's taking the string hello, which is Python specific in this case, it's language specific, and encoding it using the ASCII encoding to get the bytes that represent that string hello. And then we're going to communicate, hey, we're using ASCII, or UTF-8 in this case. We're using UTF-8, which is a superset of ASCII, and we're getting these encodings the way that we expect. So we're converting the string into its underlying bytes when it's encoded as ASCII. And we could use different encodings than ASCII or UTF-8. So we got to specify this is how we're going to encode this in bytes. And we can look at the binary if we want to. Oops, wrong one. And we can look at the binary if we want to decode these. Oh, that threw me off for a bit. It doesn't print the leading zeros. I was like, where are my leading zeros? I want my leading zeros. They're not there. So 6-8 is the first character. So this is our 8. The 1-bit is 0, 2-bit is 0, 4-bit is 0, and the 8-bit is 1. What we expect. Here the 1-bit is 0, the 2-bit is 1, and the 4-bit is 1. 4 plus 2 is 6, and we get our 6-8 from that. So our binary encoding is matching up as well. And these are the bits that we're sending over the wire or over the fiber or through our Wi-Fi. These are the bits that we're actually sending. We get these bits sent. The receiver, through our content type, we say this is UTF-8 encoded. Takes these bytes, these bits, reassembles them, and says, oh, UTF-8, I know how to speak UTF-8, and then decodes it back into a string. How do you send ones and zeros in the air like that? You'd have to take electrical engineering courses for that one. I'll just say magic. It's all wavelengths and I don't even have a off the top of my head a good explanation for that. It's all wavelengths and frequencies and stuff. It's magic. It's freaking incredible, I tell you that much. It's fascinating. But I don't have a good explanation for you off the top of my head. And I don't know how much more I want to say about hello. So let's move on to the next one. Now that homework 1 is done, are there any blacklisted libraries besides HTTP? Yeah, I mean anything that does the homework for you in general. But why would you have to wait until homework 1 was done to ask that? That's what I'm wondering. So let's take a look at another one. Let's use this UTF-8 character 1/4. No matter how hard we look, we will not find this in our ASCII chart. This is a UTF-8 only string, UTF-8 and not in ASCII. And this is what we really want to be concerned about. So let's take a look at this one and break apart its encodings. And when we encode this using UTF-8, let's see what we get. And the big thing, of course, if you've heard me say this tons of times, hopefully this is getting redundant by now, so we all know about this. But when we convert this to bytes, we're going to get more than one. So when we send this character, this UTF-8 but non-ASCII character over the internet, we have to make sure that we're aware that this is going to be multiple bytes. So this symbol, one character, this UTF-8 symbol, this character, when we encode this using UTF-8, it's actually going to be the bytes C2BC. C2BC. And remember from the slide, our continuation, did I close that? Yeah, it's not worth pulling up since I already closed it. But we can see our leading values for the bytes. So our leading values here are always 0. And then the other 7 bits are the ASCII encodings. Here, our first byte is going to start with 110, which indicates that this character contains 2 bytes of information, and then each continuation byte is going to start with 10. And we do have 8. We're using the full 8 bits of the byte, where up here only 7 are being displayed. I kind of wish it showed the leading 0, but you count them, there are 7, so there must be a leading 0 here. Here there are 8, so we have no leading 0. 110, this is the first byte of a string encoded that is encoded using 2 bytes, and then 1 continuation byte starting with 10. Is that 2 bytes inclusive of the counter byte? There's no counter byte, it's just the first bits of the first byte. So the first 3 bits of the first byte are saying, hey, this is a 2-byte encoding. These first 2 bits are saying this is a continuation byte. And then the rest of the information, all of this information, all these bits, and all these bits encode what specific character this is. So this 0000010 111100, that's saying this is the 1/4 symbol. And then the leading bits, these most significant bits of each byte, are more meta information, telling us how many bytes there are going to be. Yep, so if the first binary is 11110, and then any 3 bits after that, then that's going to be a 4-byte. And since you asked, let's just skip ahead to that one. Take a quick peek. This is going to be a character encoded with 4 bytes. So our first byte starts with 11110, saying this is a 4-byte character encoded using UTF-8. And then each of the next 3 bytes are going to start with 10 to say that these are continuation bytes. And it's important to make sure that no UTF-8 character encoding is a substring of another encoding, subsequence of bytes, I should say, not strings. The reason it's encoded like that. And then the rest of it, the 000, these bits, these bits, these bits, those bits are all telling us what specific character this is. And with that many bits of information, we can encode a lot of different characters. We can get a lot of information encoded using UTF-8. Then we could do multiple characters. I won't belabor the point too much. I think that's most of what I wanted to say here for this part. But any UTF-8 string, we get the bytes. This percent is one. Oh my goodness, my brain. 2 bytes of information. This euro sign, right? My brain just stopped working completely right now. Is 3 bytes of information, and the space character is 1 byte. But just the way that this information is being displayed to the console, it took that byte representing a space and just displayed it normally to us. So this space, it is the byte 20 in hex, but it got displayed just as a space here because it's like, oh, the console or Python or whatever along the way decided, hey, I know how to represent that byte. I'm just gonna do that. But with the UTF-8 non-ASCII characters, it just printed out the bytes for us. And we can see the decimal encodings. We have the 32 for the space, our only ASCII character in here. The %20, like you see in the in URLs to encode spaces. We can see that right here. 20 in hex is the space, the ASCII encoding of a space character. And then the binary, as we would expect. The space character being 6 only being displayed, right? So we have 2 leading zeros and then a 1 in the 32 bit place. So we can take a whole string of ASCII characters, encode them in binary, and send this over the internet. So I should have hit the punchline here. So the percent, the 1/4 symbol, the 1/4 character, this is going to be 2 bytes. So if I want to send this over the internet, and this is the big takeaway, this is what we need to know. If I want to send this character, the string containing just the character 1/4 over the internet, that's the entire body of my response. The content length is 2. 2 bytes of information is being sent in that response. So I have to set that content length to 2, or this character is not going to display to the user properly. When I get to 1/4 space euro sign, I have to set my content length to 6. I have 6 bytes of information. So my content length has to be 6, because after this string, it's only a 3-character string, but once it's encoded into UTF-8, which it has to be before we send it over the internet, because we can only send bits over the internet, once it's encoded, its encoding takes 6 bytes. Content length is 6, even though the string only has length 3. Content length is 6 because it's 6 bytes to represent these 3 characters, because we can't fit all this information into 1 byte per character. We'd be too limited. We'd have a max of 256 characters that we could represent. That's just not going to get us what we want on the modern internet. We need more bytes to represent all the characters that we want to communicate with. And we can get to 3 bytes per character. If I just want to send this character, that's 3 bytes of information. Content length is 3. What is the content length for hello? 1 byte? It's 5. You should be able to answer that, right? We got 5 bytes of information here. 1 per character. So each character is only 1 byte, but we have 5 characters, so the content length is going to be 5. So, and this is what we get away with in homework 1, is just saying, what's the length of the string? The length of the string is 5. My content length is 5. You can get away with that with homework 1 because we didn't use any UTF-8 non-ASCII characters. So the content length will be the length of the string. Each character is represented in 1 byte, and then send that as the content length. Once we have these non-ASCII characters, we can have up to 4 bytes per character. So if you have a lot of 4-byte characters in your HTML or anywhere in your document, and you're saying content length is the length of the string, up to 3/4 of your information is not being received by the client. That's a lot of your website that's just gone because you had the wrong content length. Don't make that mistake. With with a space at 6. Not for the hello. For the 1/4 space euro sign, that was 6 because we had that space. So the percent sign, where are we? The percent sign is encoded in 2 bytes. And we can decode this too. We can just look at the bytes and decode, not all the way to, we'd have to have a huge chart to look up the actual symbols. But we can see the first byte starts with 110. So the first character in this UTF-8 encoded string is going to be 2 bytes long. We have its continuation byte. So we know this is 1 character. It happens to be the 1/4 symbol. The next starts with a leading 0, because I only see 6 bits of information here. So this is an ASCII character, and I know that it's a 1 byte character. It happens to be the space character in this example. And then the next byte is a 1110 as its most significant bit. So I know that this is the start of a 3 byte character. And then I see its 2 continuation bytes here. So we have a 2 byte character, a 1 byte character, and a 3 byte character, all in this encoding. So it's 6 total bytes to send these 3 characters. Yeah, okay, gotcha. And then up to 4 bytes. So we have a 4 byte character, continuation byte, continuation byte, continuation byte. We can play with this a little. I'm just driving the point home with these examples, but we can write these byte strings directly. We can just say, I have a byte string. It's the bytes ED959C, and decode it directly. So this is what you get when you receive an HTTP request from a client. This is what you receive. Bytes. That's it. You get bytes. So we can simulate this. We could, to write testing, it can help to simulate these byte strings and build them directly. But I'm going to build a byte string and then decode it. This is what you're doing in your server. You get some bytes over your TCP connection, and you decode it using the UTF-8 encoding. So if I have these bytes and I decode it into UTF-8, well, that's this character, which we saw up here, this ED959C. We get the bytes for that character. Well, I just took those bytes and put them in a byte string right here and then decoded it into a Python string. And now I have a Python string Y containing that character, that UTF-8 character. So we can work with the bytes, and we do have to work with the bytes. It's easy to just not think about it when you're just like, oh, I have to call decode when I get a request. But I promise you, this will become more and more important as we go throughout the semester. By the time we get to WebSockets, we're actually going to work at the bit level. So you have to be very aware that the TCP connection is sending you bytes of information, which may or may not be UTF-8 encoded strings. When we get to WebSockets, it won't be. When it's an image, when a user is uploading an image to our server, it won't be. It's not always UTF-8. So we have to make sure that we understand that we are getting bytes. When those bytes represent text, we can decode them using UTF-8. When those bytes are not containing text, we do have to work at the byte and even the bit level. So we are working with bytes and bits because we have to, because that's the only things that can be transmitted over the internet. And just for fun, if we encode at hello as ASCII instead of UTF-8 and then decode it using UTF-8, of course, this works because encoding hello, since it only contains ASCII characters, encoding it with either ASCII or UTF-8 is going to give us the same bytes. So those bytes can be decoded as UTF-8 because ASCII is valid UTF-8. And nope, I don't want to talk about this. This is bit level manipulation, which we don't want to talk about quite yet. But we will That's not till WebSockets that we have to get to the bit level, which I think is fun, but we'll see what y'all think. So I did promise I'd show some. Oops, I got my comments here. I did promise I'd show some other languages today. So it's I won't go as in depth as I just did with Python, but I do want to show some other languages. In JavaScript, we have this buffer class, which is going to take a string and encode it for us. Buffer.from is going to encode a string into its UTF-8 representation. This does take an encoding, so if you want to be specific, I forgot I don't remember if it's a dash or not, or if it's case sensitive in this case. I'm just going to leave it off. But if you want to specify the encoding and be sure, actually, you know what? I have it right down here. Lowercase UTF-8. Just to make sure that it is UTF-8. Just to make sure it's being encoded using UTF-8. So let's run, and I'm going to take our string hello, encode it using UTF-8, print out the string, and then print out the encoded string. I was playing with some other stuff there. Node characters, of course, .js. And we can see that we get the bytes of that string. So this buffer is going to be the bytes of that encoding. And if we take one of our non-ASCII characters, let's grab this 4-byte character here. Let's tack it just for fun. Tack it on right at the end of hello. And we can see that we get those bytes. We get our 20 in hex, which is the space character. Space is always a character that does take up space. And then the 4 bytes to represent this character. That is a 4-byte character. It's going to take 4 bytes, and we can see this F0, A9, B8, BD, that represents that character, which, if we scroll up, we can see are the same bytes that we got in Python. This is the one huge advantage of using encodings. I'd say the advantage is that it doesn't matter what language we're using, we're going to get the same bytes. This string and the same string in Python would be represented completely different by the language. That's all language specific. But once we encode those strings using UTF-8, they will be identical. They will be the exact bytes for that character using that encoding. They'll be those exact bytes. And it'll be a one-for-one comparison. That's why we can encode things using UTF-8, send them over the internet, not even caring what's going on the other side, what language they're running, what operating system. We don't care, because we're encoding using the same encoding. They're going to decode using the same encoding, and we can communicate using bytes. That's what we want. No matter what, these bytes are going to be the same bytes, no matter who's reading or parsing, no matter who's encoding or decoding. We communicate in bytes using the same encoding, and we can effectively communicate these strings over the internet, because we're all using UTF-8. Let's head over to Java and do this. Do a quick example here. So I'm going to take, I think, that same exact character. I think I've just been cut and pasting it. Java has this getBytes method of the string class, which is going to take a string and convert it to an array of bytes. And this, again, takes an encoding. I don't remember it off the top of my head, so I'll just rely on, hopefully the default is UTF-8 here, and converts your string into an array of bytes. And then I'm going to iterate over those bytes and just print them out. This is going to format my string using a hex representation. So I'm going to print out each byte in hex, and then each on a new. Actually, let me change this to a space, so it's consistent with the other examples. But this is going to say show me this in 2 hex bits. So let me compile this Java C characters. Java characters. Obviously compiled language, so I got 2 steps instead of 1. Oh, I should have added 1 new line here. Sure. And we see those same bytes. Java happens to print out the hex A, B, C, D, E, F in capital. The other languages were doing it in lowercase. But since these are bits and it's actually binary, the capital and lowercase, that's only a difference of how it's displayed on the console to our eyeballs. That does not matter to the machine. These are the same exact bytes to represent that same character. No matter what language I'm using, same exact bytes. And for Java, this get bytes, that's what you're calling, well, we're past homework 1, so you found this out already, but that's what you're calling to send your information over the internet. When you have your string, convert it to a byte array, and then send that byte array over your TCP socket. Actually, I should look at revisit Java again. It might convert those automatically like JavaScript does in the .NET, in the net package. So with that, actually, where do I want to go with this? Well, now that I flash that, somebody's going to pause the screen on that and do that. You know, I might as well talk about it since I opened it. When you're reading files, make sure you're reading them as bytes. This will be different for each language, but make sure you're reading them as bytes. If you're ever converting your file to a string, so here I'm reading the bytes, reading all of the bytes of the file, and then I'm just copying the file over to a new file just for the sake of example here. This is going to work fine. I'm going to effectively copy this file. I'm reading all the bytes and then writing all the bytes to another file. That's going to be an exact copy of the file because all I did was read the bytes and then wrote the bytes to a new file. This is very bad. This is what some of you will end up doing in your web servers. This is very, very bad. Here I'm reading a file in bytes. This is going to be an image file. I'm reading a PNG. This is an image file. I'm reading it as bytes, which I should be doing, getting all the bytes of that file, all the bytes of the information that's encoded with PNG, with the PNG encoding, and then I'm converting that to a string. The same thing will happen if you do like read all lines or iterating over the lines or anything. You're going to get in trouble with this one. I'm converting this to a string. I'm going to use the default encoding, which should be UTF-8. But this is not a UTF-8 encoded string. This is a PNG encoded image. So this will not decode properly. This is going to give me something completely crazy, something I do not want, because it's trying to decode something that is UTF-8 that's not UTF-8. So when we're talking about the first byte of a UTF-8 character telling me how many bytes that character uses, and then continuation bytes starting with 10, there's a specific thing that says, you know, this is how many bytes, and the prefix is always going to tell us that. Well, when we have a PNG encoded file, there's no guarantee, and in fact, it's an almost impossibility that we're going to have continuation bytes and the length of the number of bytes for a character. We're not going to have that format complied with at all. So this won't even be valid to be able to convert. It will not convert into UTF-8. It's not like you'll get a random string and then you can convert it back into decode it using UTF-8 and get back to the bytes of your image. You can't do that because it's not valid UTF-8. This is when, if you've ever seen this before, when you use the wrong encoding, you get a whole bunch of just rectangles, which means there were a whole bunch of decoding errors because that was not a UTF-8 string that you decoded. So if you print this out, you just get a bunch of rectangles. Let's run this actually. Did I just do that? Yeah, I did. Copy file bad. we should see. I don't know. I don't know how much sense we'll really be able to make. Yeah, okay, that's fine. So here we have all the data of the PNG, which is the image. If I give this a .png, we should be able to see the image. I think it's behind my head. I can't see the rename option. But this file is not, these are not the same bytes for that image. Or at least I don't believe they should be. Actually, it looks like it might have just preserved all the bytes. But anyway, we don't get an image, that's for sure. We don't get the image, and we can corrupt all the bytes when we try to encode and decode like that. So don't do that. And we're 2 minutes over. The one quick thing I wanted to talk about, when you're using your net library in JavaScript, is once you do socket.write, this will take a string and then convert the string into a byte array for you. So you do have to make sure that you're given it. It will also take a byte array. So you have to make sure that you're converting these 2 byte arrays using that buffer class. Don't need that anymore. Using that buffer class the same way we did, and you can specify UTF-8 to make sure that it's UTF-8. This response is all ASCII, so I don't have to be as careful about my UTF-8. And then when you set the content length, make sure you're getting the length of that byte array. This has a byte length method, so you can just do it like that. Actually, I'm not even using this the way I set it up here. Or you can do encoded content.length after converting it to a byte array. And you have to be careful when you have your byte array. Don't concatenate that to a string, because it might convert that to a string, which is not exactly what you want.